Well, thank you all for joining us to celebrate life and achievements of Rodney James Baxter. It's a great honor for me to say a few words about his scientific work. Rodney Baxter's name is firmly associated with the most elegant mathematical discovery for at least two generations of theoretical physicists and mathematicians. I first met Rodney, as Mari said, in 1989, more than 35 years ago, during the special year in mathematical physics, which was organized here at the ANU. And that was a start of our collaboration in solvable lattice model, which has been continuing for many years. It doesn't move. Okay, so yes, so today, well, it's a very difficult job to tell about all achievements of Rodney, but I try to point out some important, how to say, milestones, and I'll briefly review the works on the main thing is the Young-Baxter equation and exact solutions of the A-vertex model, restricted solid on solid model, chiral pods model, and three-dimensional lattice models. Yes, so Rodney, in the introduction to his book, wrote, "Why do we solve these problems?" And he answers, because we can do that. And why don't we do so and see what they will tell us? Okay, so I'll make a very brief introduction in the Young-Baxter equation, consider an oriented four-valent graph and formed by intersection of the directed line, like the two I have shown here, and the pointer, yes, the pointer works. And so, and the edges carry fluctuating spin variables, which can take some number of values. And the local Boltzmann weights are assigned to the vertices. They depend on the configuration of four spins, and they're traditionally denoted by the letter R, like in the original Baxter work on the eight-vertex model. They're now called the R matrix. So the partition function defined as a sum of the internal spins and the external spins are kept fixed. So these Boltzmann weights could be different for different vertices, and it's convenient to think that they depend on two parameters associated with two lines passing the vertex, like difference of two parameters. So when the Young-Baxter equation is a statement of equality of partition function of two triangles. We just take two triangles, fix the external spin and sum over internal spins. And the left-hand side is written here, and similar the right-hand side, that one equal another. So you can write that equation in operator form, where this operator acts in a direct product of three vector spaces. So important thing of this equation, if the Boltzmann weights satisfy this equation, then the transfer matrices of the model form a commuting family. So, and more generally, the partition function of such models possess what is called Baxter Z invariance. So if you take this graph and move these lines, whatever you want, but keep the ends fixed, the partition function won't change. Some kind of topological invariance. That is what we need to know. And the first model, which has been solved using the Baxter equation, is the so-called 8-vertex model. The spin takes two values, and they're represented by thin and heavy lines. There are only 8 vertices allowed. And it's convenient, so because the ratio is only 3 parameters, it's convenient to parameterize them with the elliptic sign function of the elliptic modulus K. So we have 3 parameters, V, eta, and K, and the Baxter exact result for the free energy per site demonstrate near the critical point is this. So that is a critical singularity, and the critical exponent alpha depend on the parameter eta. And it's a nice result, but it was shocking for the statistical mechanics community because it contradicted the hypothesis of universality, which was accepted then. So the universality hypothesis states that the critical exponents should depend only on the global characteristics like dimension of the system, symmetries, but not on the details of interaction. And so from that point of view, the exponents should be, for the 8-vertex model, should be the same as the Ising model, which is alpha is equal to 0. And here, so, well, now we understand the violation of universality due to marginal operators, and which I'm not going to explain, but for some period, that was the main thing, main consequence of the Baxter work for the community. But if we look more carefully from mathematical point of view, what that solution contains. It contains the notion of commuting family of transformer and algebraic relations, Yang-Baxter equation and similar equations which are responsible for commutativity of transfer matrices. A completely new technique was introduced, functional equation for the transfer matrices. And if you look to Baxter's solution from the modern point of view, he has demonstrated that the 8-vertex model is a completely integrable quantum system possessing an infinite number of integrals. And so it took some time because before the community could realize that was a problem. But in the beginning of 80s, the papers has started to appear, particularly Fadeev, Sklanin, and Tucker, Jan in 79, designed a powerful quantum inverse problem method for solving model of statistical mechanics and field theory. And the connection to classical inverse problem method has become clear. And at that time, a classical inverse problem method was very popular in connection with the solitary waves theory. So somehow there was a quite powerful unification of the ideas from classical and quantum side of the problem. For example, classical Yang-Baxter equation, which appears as a limit which wasn't known before. And another important area is one.
Еще вопрос. Я вижу Володю и себя. Я боюсь, что даже у меня включен звук. Наверное, надо выключить. Как это?
He said that he is seeing me with the drones.
Микрофон на мут нажать. Просто кликнуть на микрофон, да?
Once again, doesn't work.
Just click with the mouse. Just click. Right click on the screen.
Okay. Oops. So, yeah, there are many things like factorized scattering theory. And so all these they created a great enthusiasm. So many people started to work on this area. So on this slide, it's just I tried to list all people who solved the Yang-Baxter equation. I'll tell a little bit later about the name of the equation, but I tried to solve the equation, and I put people who have. Surely I forgot someone. But the people who solved the Yang-Baxter equation various time, and yeah, if you count them by native language, 40% of them for somehow are Russian. The next group is Japanese, and then English and German, Dutch, Chinese, and even one Norwegian. It's Lars Zaga, who actually was the first to solve the Yang-Baxter equation. It's a star trend, a special form of the Yang-Baxter equation. He didn't know about the Yang-Baxter equation that time, 1944. But anyway, so, but formally, original work are listed at the bottom. Jim Maguire, 1964. Xian Yang, 67, and Rodney Baxter, 72. And as we've heard for Mari's lecture, in 72, Rodney with Elizabeth went to Stony Brook on the invitation by Young to give lectures about 8-vertex model. And he spent there a few months giving lecture on the 8-vertex model. But what that gets, and I asked Rodney about this, neither him nor Young recognized that they have the same equation in their work. So, and that was somehow that, and Jim Maguire wasn't there, and well, I don't know. But anyway, what was happening? But Ludwig Fadeev, who is on the picture here, together with Young and Baxter, told me the story once that C.N. Young approached him once at the conference and asked, who invented the name Yang-Baxter equation? And Fadeev replied, that was invented in our paper with Takhtajan in 1979. And Young wanted a documentary proof. So Fadeev went to the library and discovered himself, I put the quote, that the name they invented was actually Baxter-Young relation. So, but somehow with the time it was the order of the names was swapped, and the relation was replaced by equation. But you know, relation you can only verify, but equation you can solve. That is beauty. So, and then the next topic I want to cover is the conformal invariance. We'll come back. We'll return to Yang-Baxter equation later, a little bit later. But as I announced, I'll be talking about 8-vertex model, now the restricted solid and solid model. Well, in end of 70s, the Polyakov proposed the hypothesis that at critical point, statistical system should not be only scale invariant, but conformal invariant. So the conformal transformation is a wider class of transformation. And the idea was to use the conformal transformation together with operator product expansion of Kadamov and Wilson to get a solution for the field theory. But when the dimension is greater than 2, 3, 4, and so on, it's not that easy. But in 2 dimensions, the group of conformal transformation it becomes infinite dimension. And that fact helped Belavin, Polyakov, and Zamolodchikov to construct an infinite set of minimal conformal field theories and explicitly calculate the spectrum of scaling dimension for all local fields. About the same time, Baxter and Pierce, he and Kendra, solved the hard hexagon model and calculated the exponents. And later, Andrews, Baxter, and Forrester. Yeah, actually, hard hexagon was the first in the sequence of the models which were solved later by Andrews, Baxter, Forrester. But they found an infinite sequence of solvable models and calculated their critical exponents. And immediately, Hughes pointed out that these exponents match the prediction of conformal field theory. That's again Baxter work met a different approach from the field theory, and this fact caused another explosion of the activity in this area. So I found the photograph which was of Andrews, Baxter, and Forrester made in Balkov on the Baxter 2015 conference. Yeah, I put them in the right order. So now let's come back to the Yang-Baxter equation. So yeah, as I said, there are many people who are working on it and obtain different solutions of this important equation. And but do we really understand? Everything about this equation? So a lot of things has been done algebraically. For example, the notion of the universal matrix for quantized algebra, if you have quantized. I'm not going to explain what is quantized algebra, but if you have quantized algebra, you must have what is called universal matrix, which by definition satisfies this equation. And the only thing you need to do is take the algebra and calculate this universal matrix. But unfortunately, that's nearly impossible. There are a lot of work, particularly Haroshkin, Tolstoy, wrote down the formula, but the answer you get at the end is too complicated, too many summations. It's not edible. So additional insights are needed to understand that structure. And so I might have an idea, or maybe this come from extra dimensions. Suppose we have a number got a string in 26 dimensions, and by compactification to 2 dimensions, we got all the solution of the Baxter equation. But why do we need 26? Maybe 3 dimensions is enough. So are they analog of the Baxter equation in 3 dimensions? Yes, there is analog of the Baxter equation. I put it in operator and put the picture for the coincidence of the partition function of 2 tetrahedra. And the first non-trivial solution was obtained by Zamolodchikov in the context of factorized S matrix of scattering straight strings in 2+1 dimension. Okay, actually, as far as I know, there was no proof in the paper. The solution was presented, and when Rodney read the paper, he was quite excited. He described that method as an extraordinary feat of intuition. So, and Rodney had to prove, and he did it successfully. And again, if you have a solvable model and nobody can calculate the partition function, there was a one man who could all the time. That was Rodney Baxter. And Rodney Baxter calculated the partition function. So what's the relation to 2 dimensions? And in that connection, I'll start with another story. The last model on my list is called Karl-Potts model. In 1987, there was a paper by Young, McCoy, Pierre, Yan, which found a new solution of the star triangle, which is a special form of the Yan-Baxter equation relation, which parameterized by the elliptic function of genus of the algebraic curve, genus greater than 1. Okay, and that was like something extremely unexpected in the community. So everybody was excited, including myself, and of course Rodney. And Rodney with Perk and Young immediately generalized this. In McCoy's, it was 3-state model, but they generalized it for arbitrary number of spheres. And after that, for some time, there was our work. My work with Kashayev and Bazhanov and Stroganov, where we generalized it for multi-spin. For each side of the lattice, you have multiple spins. So n, by n, small n here, but each of them take n value. So when n equal 1, that would be that one. And what has happened that this generalized Karl-Potts model has a 3-dimensional. What does it mean? We can view it as a 3-dimensional model. I can tell you how that happened. And so once Rodney gave me at least two pages handwritten and said, I want to solve 3 layers of Zamolodchikov model, and wrote down a few equations on it and gave it to me. And I have a look, and I saw that one equation completely coincide with the equation we have here in our. And that after that, it has become clear that model, generalized Kyle-Potts model, is actually three-dimensional. So you take these n spins and take the two-dimensional edge and picture it like this. And the property of the interaction that it localizes and give you local structure in the third dimension. So after that, we published the paper and later on calculated the partition function exactly as in previous case. Okay, so I don't know how much time I have, but in a talk like this, I missed a lot of things which I should have said, but here I want to say that there are a couple of things which I didn't mention, that the Baxter work on the Young-Baxter equation have led to the invention of quantum group. It's quite a significant event in mathematics, for which Drinfeld was honored a Fields Medal and Jimba Wigner Medal. Discovery of invariants of knots and links by Jones, for which he was honored by Fields Medal, and a connection of gauge and string theory to two-dimensional integrable system. There are many authors, and I hope we will hear on this conference from Witten and Yamazaki about this connection. And so there, it's not, I would say that if you want to characterize Rodney's work, it's not just separate, it's something which create a very big picture, which connected with other areas of physics and mathematics. So, as Isaac Newton said, if I've seen further, it is by standing on the shoulders of giants. He was referring to Copernicus, Galileo, and Kepler. There is no doubt that Professor Baxter is a giant who brought the torch of mathematical physics into the 21st century. Rephrasing Newton, I would say, we are able to see further because of outstanding work of Professor Baxter. Thank you.